Very good morning to my boys of class 11 science. Welcome to the day 4 of the chemistry class 11 science, the chapter chemical bonding and molecular structure, chapter 4. Okay, so let us continue with the chapter chemical bonding and molecular structure. Okay, now in my previous classes, I had talked about the pi bond, sigma bond. Okay, the overlapping of the orbitals, pp orbitals, okay, sp orbitals, ss orbitals. Now today I would like to discuss with you the covalent bond formation in hydrogen, oxygen, and nitrogen molecules. Now, on your screen, you can see over there uh, hydrogen molecule. It is formed by the mutual sharing of one electron each to form a hydrogen molecule. Similarly, for oxygen molecule, two electron each to form a double bond. For nitrogen molecule, three electron each to form a triple bond. Now, in oxygen molecule, each of the oxygen atom they have a lone pair of electrons, and in each nitrogen atom in nitrogen molecule each one of them has got one lone pair of electron. Now this was covalent bond formation in hydrogen, oxygen, and nitrogen. Now coming to the characteristics of covalent compounds, they have low melting and boiling points. Okay, the first one, this is something we already know from beforehand only. Covalent compounds, they have low melting and low boiling points, because covalent compounds consist of molecules held by weak forces, and these weak forces are called van der Waals forces. These can be easily overcome by heat. These forces can be easily broken down by heat. Okay, thus covalent compounds have low melting and low boiling points. The first factor, the first characteristic is over, low melting and low boiling point. What is the main reason? Because they are held by weak forces, and those weak forces are called van der Waals forces. Okay. After that, the second characteristics of covalent compounds. Covalent compounds do not conduct electricity. That is, electricity does not pass through the covalent compounds. This is because the covalent compounds do not contain ions or free electrons. Okay. Sugar is a covalent compound and its solution does not conduct electricity. Solution of polar covalent compounds like hydrogen chloride or hydrochloric acid conduct electricity due to the presence of free ions in the solution. So covalent compounds are non-conducting in nature. That is the second characteristics. Now, solubility, the important ones I'm discussing. Covalent compounds are usually insoluble in non non-polar solvents like water. The covalent compounds, however, dissolve in non-polar solvents like benzene or toluene, which are organic solvents. The next characteristics is slow rate of reaction. In the reaction of covalent compounds, they are quite slow. This is because the covalent compounds take part in reaction as molecules, and the molecular reactions are slow. Isomerism. Covalent compounds are rigid and directional. They are rigid and they are directional. Therefore, these can give a different arrangement of atoms in space. That means we can have different structures in space. Okay. So a single molecular formula may represent a number of different compounds with different properties. This phenomenon is called isomerism. Therefore, it is possible for covalent compounds to exhibit isomerism. Okay. Now, moving to our next slide, the difference between electrovalency and covalency. Point wise, if you look at the definition, electrovalency, it is the number of electrons gained or lost during the formation of an ion from that atom. Whereas covalency, it is the maximum number of electrons that it can share with another atom to form a covalent bond. With regard to chemical bonding, electrovalency contains the formation of an ionic bond, whereas covalency explains the formation of a covalent bond. Regarding compounds, ionic compounds have atoms with an electrovalency are ionic compounds, whereas for covalency, compounds having atoms with covalency are covalent compounds. Sign used for electrovalency, we should use either positive or negative signs when indicating positive or negative electrovalency values. But in the case of covalency, there is no need to use sign when indicating the value of covalency, as it does not involve a loss or gain of electrons. So this was a comparison between electrovalency and covalency. Now moving to the next slide over here, there is a topic which is called variable covalency, which is very important in class 11. Now this variable covalency, it refers to the tendency of certain atoms to show different covalencies as a result of excitation of the atom. Okay, so when the atoms, they show different covalencies by sharing more than one electrons to form a molecule and a compound, then in that situation it is called variable covalency. In the atoms that exhibit variable covalency, the number of unpaired electrons increases as a result of excitation of atom that causes it to have variable covalency. Let us take examples to understand the covalency of sulfur. Now, sulfur we know atomic number is 16. So its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p4. So here 3s and 3p orbitals are shown over here. 3s and 3p orbitals are shown. After 3p comes definitely 3d, which is empty. Now the 3s orbital has 2 electrons and the 3p orbitals, they have 4 electrons in the ground state when it is not excited, when an atom of sulfur is not excited. Now what happens over here is when an electron from the 3px orbital is excited, it is transferred to the 3d orbital. That becomes the first excited state. So when it is excited to the first excited state, then the number of half filled orbitals becomes 1, 2, 3, and 4. So its covalency is 4. Otherwise, in the ground state, its covalency is only 2. Now again, when the next electron from the 3s orbital is transferred to the 3d orbital, then we have the 3s orbital, the 3p orbital, and two 3d orbitals being occupied singly by the electron. So there is a covalency, it can show a covalency of 1, 2, 3, 4, 5, and 6. So that is how we get to see the rise of covalency in the case of sulfur atom. Okay, so I think this is clear to all of you. Now moving to the other examples of covalency, we can see over here covalency of phosphorus. Covalency of phosphorus in the ground state. If you watch very carefully, in the ground state, phosphorus, its atomic number is, it is 15. So electronic configuration 1s2, 2s2, 1s2, 2s2, 2p6, 3s2, 3p3, 3p3. So there are 3 electrons in the p orbitals which are occupying singly. Now this is the ground state. So when an electron from the 3s orbital is transferred to the d orbital, then we get the phosphorus atom in the excited state, which have 5 unpaired electrons. The covalency is 5. Otherwise, in the ground state, the covalency is 3. In the first excited state, the covalency is 5. So sulfur, like sulfur, over here we can see phosphorus is exhibiting a covalency of 3 and 5, but we have seen already in sulfur it is showing 2, covalency of 2, covalency of 4, and covalency of 6, which you can see over here. It has been explained already in the previous slide. Now moving to the next example, covalency of chlorine. Chlorine has an atomic number of 17. Its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3s2, then 3p 1 2 3 4 5, 3p5. Okay, so there are 5 electrons in the 3p subshell. Okay, now this is the ground state. In the ground state, it has an oxidation state of -1 and +1. Okay, it can show a covalency of 1, over here. But in the first excited state, when this electron is transferred to the d orbital over here, this way. Okay, Then we have one, two, three orbitals available for bonding. Okay, available for electrons to be shared. So the oxidation state is +3 and its covalency is 3 in the first excited state. In the second excited state, the next electron from the 3px orbital, it is transferred to the d orbital. This is 3d. So now in the second excited state, the covalency of chlorine is 1, 2, 3, 4 and 5. Its covalency is 5. Again, the 3s orbital electron, it is 3s, it is transferred to the d orbital over here. Okay, and now it has covalency of 7. 1, 2, 3, 4, 5, 6, 7, where these 7 electrons can be used for sharing to form a covalent bond. So these are the covalencies of chlorine, phosphorus and sulfur, which I have explained to you all today. Now moving to the next subtopic in this chapter, which is called formal charge. The formal charge is the charge an atom in a molecule or polyatomic ion would have if all the bonding electrons were divided equally between atoms in the bond. So here I will go very slowly and try to explain you the rules for determining the formal charge on each atom in a molecule or polyatomic ion. And there will be a formula for that. But before that, let us go through the points over here. Number one, the first point is electrons within a lone pair on an atom are assigned exclusively to that atom. Half of the electrons in each bond around an atom are assigned to that atom, because in a bond, one electron belongs to one atom, the other electron belongs to the other atom. So that you have to keep in mind. Number three, the formal charges on all atoms in a molecule must sum to zero. For a polyatomic ion, the formal charges must sum to the overall charge carried by the ion, whether it is positive or negative. Okay. Now there is a formula for calculating the formal charge, and I'll explain you. I'll teach you how to calculate the formula. What do you call calculate the formal charge for a given molecule or an ion. The formula is like this. You have to learn this formula. Formal charge is equal to number of valence electrons in an isolated atom minus number of lone pair of electrons plus half into number of bonding electrons. So this is the one formula. Let us have a look at an example for the calculation of formal charges of all the atoms present in thiocyanate ion. So the formula is SCN, carrying a negative charge. Now sulfur, it belongs to group 6A. So valence electrons will be 6. Okay. The lone pair of electrons, the lone pair of sulfur thiocyanate ion, the formula is SC triple bond N. This nitrogen carrying a negative charge like this. Okay, so now the lone pair of electron on sulfur is 1, 2, 3, 4, 5, 6. Okay. Then shared bonds. There are shared bonds. Shared electron is 2. 2 electrons are shared, and that is one bond. Okay. And now if you apply the formula, valence electrons minus lone pair of electrons plus half into shared electrons. So 6 plus half into 2 is 1. 6 plus 1 is 7. 6 minus 7, it is coming to minus 1. The formal charge on sulfur is minus 1. Okay. So please go through this carefully. Okay. Again, for carbon, carbon belongs to group 4A or 14. So number of valence electron will be 4. Carbon does not have any lone pair of electrons. So lone pair of electron becomes 0. And this carbon, it has shared electrons is 1, 2, 3, 4, 5, 6, 7, 8. So 8 electrons which are shared, but total there are how many bonds? 1, 2, 3, 4. There are 4 bonds. So we have to be interested in the number of electrons. 8 electrons making 4 bonds around it. So 1 bond here and 3 bonds over here. Okay. Now, if you apply the formula for formal charge, we have 4 minus 0. 0 is for the lone pair of electrons plus half into 8 shared electrons. So that is coming to 4 minus 4, that is coming to 0. So the formal charge on carbon is 0. Then if you look at nitrogen, the formal charge of nitrogen, the valence electrons on nitrogen, it is 5. It belongs to group 15 or 5A. So it has 5 valence electrons. Lone pair of electrons, there is one lone pair of what do you call? There are 2 lone pair of electrons, sorry. Okay. 2 lone pair of electrons, and then shared electrons is 6, and there are 3 bonds over here. So if you apply the formula, we get 5 minus 2 plus half into 6, that will be coming to 0. So this is how we calculate the formal charge: number of valence electrons in an isolated atom, number of lone pair of electrons on that atom, and half into number of bonding electrons. After putting the values, we get the formal charge. So I will give you some questions in the examination, second term examination, with regard to calculation of formal charge. Okay. Now look at a more systematic formula for formal charge. Formal charge is equal to number of valence electrons in the neutral atom minus number of valence electrons around the atom in the molecule. Around the atom. So this has been opened up over here. That is equal to minus half number of electrons in covalent bonds minus number of electrons in lone pairs. So this has been subtracted. It's a better formula. This is group number. This is called group number. The group number to which the element or the atom belongs. And this one, it is called, remember that these electrons are shared by the atoms in the bond. Okay, so, or a much easier formula to remember. Formal charge is group number minus total number of covalent bonds around it minus number of electrons in lone pairs. In this way also we can calculate the formal charge. So I request you all to try to remember this formula and apply it in the calculation of formal charge. Okay. Now look at your screen very carefully. Okay. Look at the screen very carefully. On your screen you can see formal charge as applied to various molecules. Formal charge is applied to various molecules which are multiple bonded, like CNH. It has been found to be, they are calculating the formal charge of nitrogen. So it is 5 minus number of lone pair is 0 plus on nitrogen there are 4 bonds, so 4, that is coming to plus 1 on nitrogen. Similarly for the oxygen, formal charge of oxygen over here, oxygen belongs to group 6, so it is 6 over there minus number of lone pairs on oxygen is always 2, okay, plus number of bonds around it is 1, 2, 3, so it is 3, so it is coming 6 minus 2 plus 3 is plus 1 on oxygen. Similarly, if you look at NCHH over here, nitrogen formal charge of nitrogen is calculated 5 minus number of lone pairs is 4 plus 2 bonds over there, that will come to minus 1 on nitrogen atom. So these are examples to calculate formal charge as applied to what you call some multiple bonded examples. Now let us take one more example to calculate the formal charge on ozone molecule. Okay, so now you can see over here, I'll introduce one slide for that. Now O3 is ozone. O3 is the molecular formula of ozone. Now if you write down the structural formula of ozone, then we can write this way: oxygen, a double bond, oxygen, and a single bond over here, oxygen. Now let us put the electrons. This will have a lone pair, this will have 2 lone pairs, this will have 3 lone pairs, 1, 2, 3, 4, 5, 6. This is the structural formula of ozone, the Lewis dot structural formula of ozone, which you must remember. Now let this oxygen be oxygen atom 1, let this be oxygen atom 2, and let this be oxygen atom number 3. Let us calculate the formal charges on all these 3 oxygen atoms. So now for oxygen 1, for oxygen 1, for oxygen 1, formal charge, this oxygen I'm talking about, for oxygen 1, formal charge will be equal to, it is oxygen, so it belongs to group 6, so 6 minus number of valence electron is 2 minus half into total number of electrons 1, 2, 3, 4, 5, 6, so half into 6, that is coming to, it is coming to plus 1. So formal charge on oxygen 1, it is coming to plus 1. Okay. Now for oxygen to the second oxygen, this oxygen. Okay, formal charge. Formal charge. Again, 6 is the group number minus number of lone pairs. Number of lone pair is 4 minus half into number of bonding, non-bonding electrons total. You can check over there 1, 2, 3, 4. Okay, so it is coming to 4 over here. If you simplify this, you will get the formal charge on the second oxygen as 0. Then for the next oxygen, that is oxygen atom number 3, the formal charge is equal to again group number 6 minus over here there are 1, 2, 3, 4, 5, 6 electrons. 6 electrons minus half into 2 electrons are bonding electrons. So I can put over here 2. So that will give me again over here the formal charge for the third oxygen as, just check over there, it is coming 6 minus half into 2, that is coming 2. So it is coming to -1. So these are the formal charges on oxygen 1, oxygen 2 and oxygen 3. Okay, so that is very important to understand over here. Over here just check the answer. 2 minus 3, here it will be 1, 2, 3, 4. So I think this has to be 4 over here. So half of 4 becomes 2. 2 minus 2, 0. It has to be 6 only, sorry, because there are 1, 2, 3, 4, 5, 6. We have to consider this electron also to calculate the formal charge of the first oxygen atom. Okay. Now, so practice some more examples from your textbook with regard to calculation of formal charge based on their what you call Lewis structural diagrams. Now, moving to the next slide, let us come to Fakans rules. Now, Fakans rules was given to understand the extent of polarization in covalent compounds. Now, here let us discuss the factors first. The factors which govern the extent of polarization and the corresponding rules are given below. Size of ions. First factor is size of ions. Smaller the size of cation must be small, and greater the size of anion, greater is the extent of polarization in an ionic compound. Okay, that is polarization. First factor is size of ion. Then the charge on ions. Larger the charge on cation, if the cation is large in size, and anion is also there having a larger charge, greater will be the extent of polarity. That means ions carrying larger charges, they are more tending to be more polarized. Okay, polarized means separation of charges. The third one is electronic configuration of the cation. A cation with an outer electronic configuration of the type S2p6d10. If there is an outer electronic configuration containing d orbitals also, electrons, it will possess a greater polarizing power as compared to that cation having the same size and same charge but having outer electronic configuration of the type S2p6. Okay, so please keep this in mind. This is very important point where the factor is very important. And the fourth one, dielectric constant of the medium. Dielectric constant means the medium which is what do you call which is going to what do you call this dielectric constant means the medium which will prevent prevent the conduction or movement of charges. Okay, that is dielectric constant. Here, if the dielectric constant of a medium is high, if it is high, that means any medium which does not allow the movement of current or electrons, that is tend to have a dielectric constant. Okay, so higher the dielectric constant of the medium, lesser will be the extent of polarization in an ionic compound. That means for an ionic compound to be more polarized, the dielectric constant must be low. So this has to be remembered. So these are the factors which I will request you all to go through and try to remember. Okay. Now moving to the next summarized Fakans rules. If a small cation means the covalent nature is high. If the cation becomes large, the covalent nature decreases. If there is small anion, covalent nature is less. If the anion becomes large, the covalent nature increases. Low charge means covalent nature is less. If there is high charge, covalent nature is high. So this is a summarized of one or two points from the previous slide. Moving to the next slide, with respect to the Fakans rule, the feasibility of having some covalent character can be predicted by using Fakans rules. A compound is likely to be covalent if cation has small size, high charge. Learn this. Okay, please learn this. A compound is more likely to be covalent if the size of the cation is small and it is carrying a high charge. It is highly polarizing and attracts electrons in the anion towards itself. If the anion has large size and also high charge. So ultimately, for a covalent molecule, for a compound which is covalent to be more polarizing, more covalent in character, it must have small size, the cation small size, high charge, anion large size, high charge. Then only it is polarizable and will be easily distorted. Just because a substance is less likely to be covalent according to Fakans rule doesn't mean it will be ionic. It will remain covalent, but will have some ionic character in it or vice versa. Okay. Now, moving to the next subtopic in this chapter, which is called resonance. Resonance, which you have learned in organic chemistry, delocalization of pi bonds. Delocalization of pi bonds along a conjugated system. Conjugated system means system having alternate single and double bonds like this, that is a conjugated system. So a molecule or polyatomic ion for which two or more Lewis formulas with the same arrangements of atoms can be drawn to describe the bonding is said to exhibit resonance. Now have a look at this carbonate ion. If you look at the carbonate ion very carefully, you will see over there carbon in the center surrounded by three oxygen atoms. This oxygen has three lone pairs. This oxygen has two lone pairs. This oxygen has three lone pairs. And the overall charge carried by is -2. Now this bond is a sigma bond and a pi bond. So the pi bond resonates between this bond and this bond. So in the next resonating structure, this pi bond has shifted over here. So it is shifted. The overall charge remains the same. So this movement of the pi electrons along the single bonds, it is called resonance. So this has been explained with the help of by the help of taking the example of carbonate ion, CO3 -2 ion, and it is important that you remember the structure, these resonating structures of carbonate ion to understand resonance. Now look at some examples on your screen. I have drawn examples showing resonance in carbon dioxide and ozone. This one is carbon dioxide, this one is ozone. Okay. Now, we have already seen that time the formula, the structural formula of ozone, where this oxygen it has two lone pairs. This oxygen it has a lone pair. We calculated plus one, and this oxygen has one lone pair, two lone pair, and three lone pair. Okay, third oxygen. Okay, now this can be understood very clearly. Okay, so over here again I'll put two lone pairs. This will have a lone pair. This will have three lone pairs. Okay. Now, firstly, let us discuss about carbon dioxide. In carbon dioxide, this is the structural formula. Carbon linked to the two oxygen atoms by means of a double bond. One is pi, one is sigma bond. Pi bond, sigma bond. Now, what happens over here? If this lone pair is falling on this bond over here, it will form a triple bond, and this oxygen will carry a positive charge. It will carry a positive charge. Whereas if this oxygen, then when this falls over here, this pi bond will shift to the next oxygen atom. So it will make it a negative charge. So this happens the other side also. Okay. So this is called resonance in carbon dioxide. If you look at the resonance in ozone molecule, this pi bond will shift over here, will give make it a double bond, and that time this will have a what do you call single bond. This will have a double bond. So this movement of pi electrons, it becomes what? It becomes resonance. Now looking at few more examples for resonance in nitrate and carbonate ion. This one is nitrate ion, NO3 minus 1. This one is carbonate, which you have seen already that time. Okay. So here also you can see the movement of these pi electrons across this and across this single bonds. Okay. See over here. Similarly, the resonance in carbonate ion. Try to remember these structures. Okay. Now, moving to the next subtopic in this chapter, which is called coordinate covalent bonds. Now, we have learned or heard these coordinate covalent bonds in class 10 as well. They are also known as dative bonds, also called a dative covalent bond. It is a covalent bond in which both electrons come from the same atom. This is a definition which you have learned. So, if you look at an example over here, carbon monoxide molecule, these dots are in the same color, which means these two electrons belong to oxygen. So these two electrons have been contributed by this oxygen. So that becomes a coordinate bond. So this is how to represent a coordinate bond in a covalent compound. Now, moving to our next slide, the next thing in this chapter, some oxo acids of chlorine. I request you to remember the structural formula of some oxo acids of chlorine. Okay, this is important. This is important for you all, very, very important. Okay, don't take it very easily or lightly with regard to this, some oxo acids of chlorine. Now, here the first oxo acid of chlorine which you can see on your screen, it is perchloric acid. Perchloric acid. It is what? Perchloric acid with the formula HClO4. HClO4. It is HClO4. And this bond is coordinate. This bond is coordinate. Okay, these two bonds are coordinate. Okay, bonds. That is perchloric acid. The formula is HClO4. HClO4. Perchloric acid. Okay. Then the next one is chloric acid. Next one is chloric acid. The formula is HClO3. Molecular formula and the structural formula you can see HClO3. And in perchloric acid, there are again two coordinate bonds. This one is a coordinate bond and this one is also a coordinate bond. Okay, so here in perchloric acid, you'll see the oxidation number of the central chlorine atom is +7. In chloric acid, the oxidation number of the central chlorine atom is +5. Okay, variable covalency. Then the third oxo acid of chlorine is chlorous acid. Chlorous acid has a formula HClO2. HClO2. If you look at chlorous acid, the central chlorine atom has oxidation number +3, covalency is 3. Okay, and it also has a coordinate bond, and the coordinate bond is this one. Okay, then the next oxo acid of chlorine is hypochlorous acid. HOCl. It is what? It is HOCl over here. Now, here this chlorine atom, it has what? Oxidation number +1. So these were some oxo acids of chlorine, which is on your screen for you. Now, have a look at the coordinate bond in ozone molecule. You must be wondering which is the coordinate bond over here. Now, in this coordinate bond in ozone molecule, you can see this side there is a sigma bond, there is a pi bond. This oxygen has 2 lone pairs, this oxygen has also 2 lone pairs, this has 3 lone pairs. Okay, but remember this bond which is over here, it is supposed to be a coordinate bond. Okay, so there are, you can see total altogether there are 2 sigma bonds, one here, and there is 1 pi bond between these 2 oxygen atoms. Okay, now moving further to our next slide with regard to, over here you can see it is sulfur trioxide molecule. You can see the coordinate bonds have been marked. Okay, here and here coordinate bonds have been marked. Sulfur trioxide molecule, SO3. Okay, the next one is coordinate bonding in sulfur dioxide molecule. Coordinate bond is marked. Next is over here ammonium ion. Ammonium ion. This we have learned in class 10 as well. We have learned in ICC class 10. Formation of ammonium ion. when a lone pair of electrons on the nitrogen atom associates with the hydrogen ion using its lone pair of electrons, then it forms an ammonium ion in which there is a coordinate bond. The next one is formation of hydronium ion, coordinate bond over here. Okay, so these examples you should be able to draw when it is asked in the examination. Now, moving to our next slide over here, on your screen you can see some examples of molecules where there is coordinate bond. Where there is coordinate bond. For example, this one is sulfuric acid, H2SO4, sulfuric acid. Actually, you can see sulfuric acid. Okay. H2SO4 coordinate bond is here and here. Okay. The next example which you can see, it is nitric acid. This one is nitric acid, HNO3. And in nitric acid, if you see the coordinate bond, it is this one. This is the coordinate bond. Okay, this is the coordinate bond. Please try to remember that. Then the next one is H3PO4. H3PO4, phosphoric acid. H3PO4, phosphoric acid. Okay, it is H3PO4, and the coordinate bond lies over here. Coordinate bond lies over here. Okay, it is on this oxygen atom. Next one is a very important formula, very important, and I have seen plenty of questions based on this ammonia boron trifluoride complex. Ammonia and boron trifluoride, they combine with each other by means of a coordinate bond, and the coordinate bond lies over here. It is a complex. It is called ammonia boron trifluoride complex. When the lone pair of electrons on the nitrogen atom from ammonia molecule uses its lone pair and coordinates with the boron atom of boron trifluoride, then it forms a complex, because this boron is deficient of electrons. It is deficient of electrons, though it is showing incomplete octet and it is still stable. It is in what you call incomplete. It is short of electrons to an octet. That is why it is capable for the ammonia molecule to form a bond with boron trifluoride to give a complex which is called ammonia boron trifluoride complex. Okay, I think this much is clear to all of you. Now, my dear students, let us see. Okay, there is some more time left. Okay, now if you look at the next screen, this is hydrogen bond. Hydrogen bond. On your screen, you can see there is hydrogen bond. Hydrogen bond, it is an interaction. It is an interaction between a hydrogen atom attached to an electronegative atom and an electronegative atom which possesses a lone pair of electrons. The strongest hydrogen bonds involve the first two elements, that is fluorine, oxygen, and nitrogen. Okay. Now, let me give you some examples. Suppose we have a lot of water molecules together. Lot of water molecules like this together. Okay. So if there is an interaction between the oxygen of one water molecule and the hydrogen of other water molecule, this interaction is called a hydrogen bond. And the very fact a hydrogen bond is formed between the oxygen and hydrogen of two different molecules of water accounts for the existence of water in the liquid state, at ordinary room temperature and pressure conditions. We can see hydrogen bond which is slightly weaker in the case of hydrogen fluoride. Talk about that also. Hydrogen fluoride, this way, hydrogen fluoride. Okay, so you can see fluorine electronegative atom and hydrogen from the other atom. Okay, so this is also a hydrogen bond. So this hydrogen bond which you are seeing on the screen, it is a case of intermolecular. It is a case of intermolecular hydrogen hydrogen bond. Okay, so now with this, I will explain you one more type of hydrogen bond which is called intramolecular. Let us have a look at this example. Phenol, an organic compound like this. Within the same molecule, if I have something like this, okay, C, O, okay, then O over here, and then H over here, okay, okay. Now, It is a carboxylic acid. So if there is an interaction between this oxygen and the hydrogen, this is a carboxylic acid group, COH group. In the same molecule, within the same molecule, if there is formation of hydrogen bond, this bond which is formed, it is called a it is called a hydrogen bond. So when such hydrogen bond arises within the same molecule, it is called intramolecular. It is called intramolecular hydrogen hydrogen bond. Intramolecular hydrogen bond. So with this, I would like to end my class over here only. In the next class, I will be discussing the conditions for effective hydrogen to take place. Okay, so thank you so much. Have a nice day.